So this is the video lecture on sampling distributions and the central limit theorem. So to start with, if you remember back when we were talking about random variables, we said that anything is a random variable if it depends on the particular thing that we sample. So if you remember also, x bar is the sample mean. So if we pick a different sample, we could get a different sample mean. So what that tells us is that x bar is a random variable. Every random variable has a distribution, a mean, and a standard deviation. So in this section, what we're going to talk about is the distribution, the mean, and the standard deviation of all of the possible values of the sample mean. And that's what the central limit theorem tells us. So let's suppose, to start with, that we take a sample of size n. So n is going to be our sample size from some distribution. Doesn't matter if it's normal or not for now. The distribution has a mean of mu and a standard deviation of sigma. We don't know what those values are just yet, but in individual problems we'll be plugging in values. If we were to take a sample of size n, the mean of that sample could take on a whole range of values. Some of those are going to be more likely than others. The mean of this distribution of sample means, so of all of the possible sample means we could take from a population, the mean of all of those is mu sub x bar. Okay, it's mu with a subscript of x bar. And the standard deviation of that distribution is sigma sub x bar. So the central limit theorem tells us three things. First of all, it tells us that the mean of all of the possible sample means is the same as the mean of the population. So in other words, mu sub x bar is the same as mu. So if I tell you what the original population mean is, that's telling you also what the sample means are centered around. That should make sense to you if you think about it in terms of the sample mean is a pretty good estimate of the population mean. So if you found a sample mean, you'd expect it to be sort of centered around the population mean. So the next thing the central limit theorem tells us is that the standard deviation of the x bars is the standard deviation of the original population divided by the square root of the sample size. So the standard deviation, so this tells us that the sample means are going to be a little bit less spread out than the original population. And if you think about it, every time we take a sample mean, we're taking the center of a sample. So if you compare the sample means to the original population, you would expect that the sample means would be a little bit less spread out than the original population. So that's the second thing it tells us. X bar follows approximately a normal distribution as long as one or both of the following two things are true. First one is that the original population being sampled is normally distributed. So if we know that the original population being sampled follows a normal distribution, x bar follows a normal distribution. Period. If we don't know that, we can still use the normal distribution for x bar as long as the sample size is large. And large, usually we're referring to at least 30. But the larger the better. So this is just to summarize, where we can compare, if we're looking at the original population being sampled, that has a mean of mu, standard deviation of sigma. It may have any distribution, And we're going to sample n items from this original population. Once we do that, the distribution of the sample means has a mean of mu, standard deviation of sigma over the square root of n, and regardless of what the original distribution was, if we have a large enough sample size, x bar follows a normal distribution. But even if we don't have that, if we have a small sample, the population being sampled, and we know that the population being sampled follows a normal distribution, then we can still use the normal distribution with x bar. So I know that all of that is sort of theoretical up to this point. But this is going to allow us to use, to find probabilities associated with x bar. And this is going to come in really handy when we do inferential statistics. So let's start with an example. We looked at this example, I think in the last section. The high temperature in June is normally distributed with a mean of 80 degrees Fahrenheit and a standard deviation of 4 degrees. If we randomly sample 20 June days, does the sample mean follow a normal distribution? The answer here is yes. So even though we've only got 20 observations, which is less than 30, you're told that the original distribution is normal. Because of that, we can say that x bar follows a normal distribution. Okay, and that goes back to here. You're told that, it's right here, the original population being sampled followed a normal distribution, therefore x bar follows a normal distribution. The mean and the standard deviation are mu sub x bar is 80, because that's what the original population mean was. And the standard deviation of x bar is sigma, which we said was 4, over the square root of the sample size of 20. Okay? So far, what we've done is we've characterized the distribution. We've said it. We know it follows a normal distribution with a mean of 80 and a standard deviation of 0.8944. Well, now that we know that, we can use the normal distribution to find a probability. So we want to find the probability that the sample mean is between 78 and 82. Okay? Well, previously when we were trying to convert from x to z, we used x minus the mean of the x's divided by the standard deviation of the x's. Well, now we're doing something similar, except it's x bar minus the mean of the x bars divided by the standard deviation of the x bars. Okay, so if we're trying to find probabilities with x bar, we're going to use this formula. So x bar minus mu sub x bar over sigma sub x bar. So we need to convert 78 and 82 to z by subtracting mu sub x bar, which we know is 80, and dividing by sigma sub x bar, which we said was 0.8944. When we do that, we get plus and minus 2.24. All right, we do that. We go over to the StatCrunch normal function, type those two values in, and we get 0.9749. Okay? And so that's what our answer is, 0.9749. So I put a note in here, just like for the previous section, I want you to convert to the standard normal, even though, yes, technically you could plug in the mean of 80 and the standard deviation of 0.8944. This is another place where I want you to show me that you understand how x bar converts to z. All right, let's do a second example. So at large schools, the mean number of people who withdraw from introductory statistics classes, let's say is 18, with a standard deviation of 4.2. Let's suppose we take a sample of 36 classes, and we want to find the probability that the sample mean is more than 20. So in other words, we're going to find the probability that the mean of a sample of 36, that's X bar, is greater than 20. So first of all, can we determine that X bar follows a normal distribution? So can we use the normal distribution with this problem? The answer is yes. Because even though they don't tell you what the distribution is of the original population, they do tell you that the sample size is large. So because of that, we can use the normal distribution for X bar. So the mean there is the mean of the original population, which was 18, and the standard deviation is going to be the original standard deviation, 4.2, divided by the square root of the sample size. So 4.2 over the square root of the sample size gives you 0.7. All right, so we know that X bar follows a normal distribution with a mean of 18 and a standard deviation of 0.7. So now we can find the probabilities. So if we wanted to find this probability, we would convert to z by doing 20 minus mu sub x bar, which we just found to be 18, over sigma sub x bar, which we found to be 0.7. That gives us 2.8571. And if we go to StatCrunch's normal distribution function, we get 0.0021. So would that be unusual? Yeah, the probability is really small. It's usually, we use 0.05 as the cutoff. Therefore, that would be unusual if we took a sample of 36 introductory statistics classes and we found the sample mean was 20 or greater. One more example. Still looking at the example where the mean number of people who withdraw from introductory statistics classes at large schools is 18 and a standard deviation of 4.2. What would be the probability that one individual class would have more than 20 students withdraw? For this problem, we need to assume a normal distribution. The reason I'm giving you this example is to show you that this problem is not a central limit theorem problem because it's not the probability of a sample mean. This is just the plain old probability relating to x, which is like what we did in the previous section. So this is probability that x is greater than 20 because it's just one observation, not the mean of a bunch of observations. So we would do that the same way we did in the previous section, just subtracting the mean, dividing by the standard deviation, and then plugging into StatCrunch and get 0.3170. All right, so that's it. That's it for this section.